Okay, so we're back again, and this time we are doing 1.1.2D we're doing distillation, and it's the one after crystallization. It's a bit dark in here, I know, it's night, because it literally took 6 hours to upload the previous video. But anyway, imagine we mix liquids together, for example alcohol and water, and when we mix the alcohol and the water together, they completely mix to form another solution, and you can't really see the alcohol in there, right? But there is a way to actually separate those two liquids even though they've completely dissolved into each other. So liquids of different boiling points, okay, so that's the key thing, can be separated using distillation. For example, a mixture of ethanol, this is the formal name for alcohol, okay, which has a boiling point of 78 degrees Celsius, and water, which has a boiling point of 100 degrees Celsius, can be separated in this way. Below is a typical setup for distillation, which is this thing here. Just ignore what I've drawn here. Okay, we're going to come back to that. It's pretty elaborate, okay, and a lot of you might not have seen this before. Imagine we have a mixture of water and ethanol. These are clearly miscible. Miscible is a word that means dissolvable, okay, within each other. We use the word miscible to describe liquids that can dissolve within each other, and gases as well, okay? So, having a look at this, I'm going to just elevate that a little bit. What we have is a Bunsen burner, and it's got an open hole, which means the flame is going to be hot. Then what we have is this bit here. It's called a pear-shaped flask because obviously it's shaped like a pear. Sometimes instead of a pear-shaped flask, what we have is a round bottom flask. Okay, if you remember in the what do you call it? That worksheet of apparatuses, it should be in there. And then we have this piece of glass. I haven't really labeled it, but it's called a still head. Okay, so still head. This is actually a little bit advanced, okay, in labeling this. Then we have a thermometer where the bulb is sitting right there at the entrance to this funny looking thing, and by the way, it stretches from here to here, and it's called the condenser. Now what this condenser is it's all made of glass, okay, and it's a tube, and it's got a glass jacket on the outside, and we allow water to run through the glass, okay? So basically this is a rubber hose, and water from the taps come in, and they go through and they surround this tube. They never enter the tube, by the way. They surround the tube, and the water goes out at the top, and this will obviously go to the sink, okay? Now what this does, and this is what I said in the lecture, it makes it cold. It makes this tube cold, and that's what running water does. Running water makes things cold, and that is why, and I talked a little bit about Koreans going camping, and if they have like a watermelon or a melon of any kind, what they do is they put the watermelon in the riverbed where the water is running, and it's not to wash the watermelon. Obviously we don't eat the skin, so there's no point in washing the watermelon, but what it does is that it keeps it cool. And that's the same story here. And water goes in from the bottom to the top. You always have to remember that, okay? And then we have a measuring cylinder. We don't always have a measuring cylinder. We can just have a beaker or something like that. Yeah, so, okay, that's the general setup, okay? Now, what happens is you've got the mixture in here, okay? The mixture of water and ethanol, okay? And it's boiling, and we make sure that at this point here, it does not go over 80 degrees Celsius. And the reason why that is because we remember that ethanol has a boiling point of 78 degrees Celsius and water has a boiling point of 100 degrees Celsius, okay? So at 80 degrees Celsius, at this point, it'll be hotter here. These guys, they'll vaporize, okay? So basically the ethanol will vaporize out first, and it'll still be a gas here, but water vapor will be like, oh, it's not a gas at 100 degrees Celsius, at 80 degrees Celsius. It should be a gas at 100 degrees Celsius. So basically it'll fall back down. But ethanol will come out and say, oh, wait a minute, it's 80 degrees Celsius. I'm going to keep going. And then it comes to this point and it goes through the condenser, but this is cold. If you remember, we've made it cold. And any gases that touch a cold surface will start to form droplets. It'll condense and form droplets of water. So that's what these little warts were before, okay? These were droplets of ethanol. And then they form liquid together and they pour down into the measuring cylinder. And that's what's going to contain. It's going to contain the ethanol. In general, it is called the distillate, okay? Just like in filtration, it's called the filtrate. Over here, this is called the distillate. Okay, so let's just go over this again. At 80 degrees Celsius, and that's why we need the thermometer. You need to make sure that it's at 80 degrees Celsius. The ethanol goes up as a vapor, as a gas, and it'll pass through and it'll form droplets again in the cool surface, inner surface of the condenser, and then it'll fall down as a liquid. And that's how we're going to separate water and ethanol, because what's left behind here would be water, okay? And that's what distillation is. It's a really interesting and very useful apparatus to separate mixtures of liquids. But this is not perfect, let me tell you that. Okay, so I'm going to read here. Unfortunately, a simple distillation apparatus, scientific equipment, does not work perfectly. If we distill a mixture of two liquids such as alcohol and water, which do not have greatly differing boiling points, unfortunately, this is still not different enough. Then the distillate, which is the substance that has been evaporated and condensed back to liquid, is actually not a pure substance. Instead, the distillate is a mixture, but generally it is richer in the lower boiling point component, and in this case, ethanol. So basically, over here, what we'll have is a lot of ethanol and we'll have some water. Unfortunately, some water vapor escapes right through along with the ethanol, because water starts to actually vaporize from 50 degrees Celsius, okay? So it's going to have a richer amount of ethanol, but it won't be pure, okay? So that's the problem with this apparatus. It's not perfect, but it is perfect if the temperatures were different enough. But unfortunately, 78 degrees Celsius and 100 degrees Celsius is not perfect enough. Okay, so where were we? All right. A mixture of 15% ethanol and 85% water, when it's distilled, produces a distillate of about 40% ethanol and 60% water. So, okay, fine, the percentage increases, but it's still not separate, okay? Therefore, these substances are not completely separated at all. So when should we use distillation? A mixture of two or more liquids can be separated by distillation if the boiling points of the liquids are sufficiently different, for instance, differing by about 40 or 50 degrees, okay? For example, distillation of a mixture of water and ethylene glycol. Now, ethylene glycol is also known as antifreeze. Okay? And what it does is it prevents water from freezing. It's a very interesting substance. I'm running a little bit out of time, but I'll tell you what it is. Just imagine you're in Canada, okay? You live in Canada and it's always cold and everything's like basically frozen. So what happens if you park your car outside in Canada? Your engine will actually freeze, okay? So in order for the petrol and the water in the engine to, by the way, water is not inside the petrol, let me just get that clear, okay? In order for the water not to freeze, they mix it with ethylene glycol, because obviously, oh, excuse me, I sneezed. Obviously, if you have ethylene glycol, it won't freeze, and therefore your car will run at very low temperatures. Okay, so basically a mixture of that with water produces pure water as the distillate and leaves, I'm going to sneeze again. I cough in the previous video and I sneeze in this one. Oh dear. Okay. Produces pure water as a distillate and leaves the glycol behind in the distillation flask. Okay, so that's because they're very different in boiling points. This happens because the boiling points are so different. 100 degrees for water and 198 degrees Celsius for ethylene glycol. That is, water is more volatile, and volatile means it's more easily able to be converted to a gas, and the other way around, by the way, than ethylene glycol. So very quickly, also, if a mixture of a volatile liquid, volatile means it's easy to turn to a gas, with non-volatile solids such as sand and water is distilled, the distillate is a pure liquid. Yeah, obviously, because sand won't vaporize, okay? It'll stay in here. You'll have sand here, water here. If a mixture of two liquids of comparable volatility, similar boiling points is distilled, the distillate is generally richer in the more volatile liquid, such as in the case of water and ethanol, and we talked about that before. Now, this is pretty important, okay? Sometimes when we want to obtain a dissolved solute, for example, salt or copper sulfate, because it dissolves in the water, a usually solid substance that is dissolved in water without losing the liquid in which it is dissolved, we can also use distillation. So that's when you don't want to lose water. For example, if we have a solution of copper sulfate and we wish to obtain only dry copper sulfate crystals, then evaporation is appropriate. However, if we wish to retain both copper sulfate and water, we can use distillation. Pretty interesting. In this case, solid copper sulfate crystals will remain in the pear-shaped flask, and the distillate is water, therefore retaining both a solute and solvent. Okay, which means the liquid the solute is dissolved in.